Hi folks, the video was getting a little long, so I decided to do the problem practice in a new video. So this is the continuation of the lesson on using the lens equations, and this video I just work out 3 example problems for you to do. So hopefully help out, and remember, if you have any questions, online chat Monday, Wednesday, Friday at the website, and you can of course email me anytime. So let's take a look and solve a couple of lens problems. Alright, so first question. A theater projector uses a lens with a focal length of 9.93 centimeters with the film placed 10 centimeters in front of the lens. What kind of lens is being used? In part B, where should the movie screen be placed so the image is focused? And C, how magnified is the picture? So when you go to, well, nowadays most movie theaters are digital. There are still some film theaters out there. So a movie camera would work by taking an image from the film and projecting it onto a large screen. Well, since I'm shining an image on a screen, that means that image has to be a real image. So that tells me what kind of lens I'm using. Ooh, let me go back, sorry. So the lens for part A, I have to have a convex lens. I have to have a convex lens because that's the only thing that makes a real image. Alright, so as soon as you're projecting the image, you know you're dealing with a convex lens. That's important because that tells me that my focal length must be a positive number. So where should I place the movie screen? What I'm looking for is where the image should be, so what I'm looking for is Q. So for part B here, what I'm trying to find is what Q is equal to. Well, they tell me the focal point, or the focal length, is equal to 9.93 centimeters. Since this is a convex lens, I know that this is a positive number, so plus 9.93. The film is placed 10 centimeters in front of the lens. Well, the film is what I'm projecting through the lens. The film is my object. So, and again, all our objects are real. So P here is plus 10 centimeters. All right, so I have the focal point. I have the P. So this is actually fairly straightforward to solve for Q. The lens equation says that 1 over F is equal to 1 over P plus 1 over Q. All right, I'm going to rearrange. I'm going to get Q by itself. So, but first I have 1 over Q equal to 1 over F minus 1 over P. All right, so I could now basically just stick in the numbers if I wanted to. I could do a common denominator. We did it with mirrors. This one I'll just put in the numbers. So I have 1 over 9.93 minus 1 over 10. Now, if we do this, I get 1 divided by 9.93, enter, minus 0.1, enter. I get a really tiny number. This works out to be 0.0000705 or so. Now, it's a really tiny number because I haven't solved for Q yet. This is equal to 1 over Q. So that means that Q is going to be equal to 1 divided by 0.0000705. And when I do that out, Oh, this works out to be roughly, about 14, 20 centimeters or so. 1,420 centimeters. Well, that's about 14 meters. Or roughly 14 meters would be about, somewhere between 45, 48 feet. Which kind of makes sense because the movie screen is quite far from the projection booth. So there you go. So the key piece is remember that when you solve the equations, you're solving for 1 over q. You have to remember to flip it when you're done. Now for C, if I want to know the magnification, well, generally the magnification is equal to the height of the image divided by height of the object. But remember that also equals minus q over p. So that would be equal to minus 1420 divided by 10, or about the magnification here is minus 14.2. That means 142. So that means the image on screen is 142 times the size of the image on the film. Well, that makes sense. Film is small, screen is big. The negative sign means the image is upside down. Now, you might object to that, but what you got to realize is if you look at the film and the camera, they actually load the film so the picture's upside down, so when they project it, the image is upside right. So there you go. All right, so pretty straightforward. We use the lens equation. And we use the magnification equation. Really, the tricky bit is remembering what the signs. All right, let's look at another problem. All right, so a concave lens with a focal length of 6 centimeters is used to look at a 2 centimeter tall beetle that is 3 centimeters from the lens. How tall is the image of the beetle? And is this the right lens to use? Well, how tall is the beetle? So let's start making a list of variables. So how tall is the beetle? Well, that's a height. So what I'm looking for is I want the height of the image. The beetle is 2 centimeters tall. So I know the height of my object is 2 centimeters. All right, well, what else do they tell me here? The focal length is 6 centimeters. Now, this is where the problem is tricky. This is a concave lens. So my focal point is 6 centimeters. But it's a concave lens. It's a diverging lens. I have to notice that because this focal length needs to be negative. If I use a positive 6 with this problem, the math will work out incorrectly. And my answer will be wrong. So with that said, how am I going to get this height of the image? Well, if I knew the magnification, I could do it. The magnification, again, is equal to HI over HO. So if I can find this magnification, I can find the height of the image, since I have the height of the object. But remember, this is also, the magnification is also equal to minus the distance to the image Q over the distance to the object P. So if I can find out what, now they're telling me that the beetle is 3 centimeters from the lens, so I know that P is equal to 3 centimeters. Now, this is a real object in front of a lens, so the P is positive. It's only the negative is only coming into the focal point because of the type of lens I'm using. So if I have F, I have P. So if I can find out what Q is, I can get the magnification, and then I can find the height. So let's write down the lens equation again. I have 1 over F equals 1 over P plus 1 over Q. So I'm going to solve for this 1 over q by subtracting the 1 over p over. All right, well, I can now stick in my numbers. That means that 1 over q is going to be equal to, well, that's 1 over minus 6 minus 1 over 3. Now, that's the same thing as saying that 1 over q is equal to, well, I have a 6 and a 3. I better make a common denominator 6. So I have minus 1 over 6 minus 2 over 6. Well, and this is where that negative sign is so important. I have a negative fraction minus a fraction. That means that these two negatives are going to add. So 1/6 and 2/6 is going to be equal to minus 3/6. Or minus 1/2. But again, that's 1 over q. So if this is if 1 over q equals minus 1/2, that means q must be equal to minus 2 centimeters. So q equals minus 2 centimeters. So the beetle started, the object was 3 centimeters from the lens. The distance to the image is 2 centimeters. The negative sign tells me that this is a virtual image. So the negative sign is okay and has important information. That means that the image will be upright when I'm looking at it. But let's address, is this the right lens to use? Well, to get that, then let's finish the problem by finding the magnification. All right, so the magnification is going to be equal to minus 2 divided by p, which was, sorry, I'll just put p in, minus 2, p was 3. So my magnification is equal to 2/3. That means the height of the image is 2/3 times 2 centimeters, or 4/3 of a centimeter. Well, if I'm using the lens to examine something, this is telling me that the image I'm going to see is actually smaller than the object. It's smaller. The image of the beetle is smaller than the beetle. So this is not the right kind of lens to use. If I want to look at something, I don't want to use a concave lens because the image is always going to be smaller than the object. So why would I use a concave lens to make it harder to see what I'm looking at? So, but again, equations are simple. It's just magnification equals hi over ho, and 1 over f equals 1 over p plus 1 over q. The tricky bit was remembering that the focal point had to be a negative number because it's a concave lens. All right, so given that I don't want to use a concave lens to look at an object, what should I use if I want to make it easy to see an object? Well, I want to make a virtual image that, generally if I'm examining an object, I'd like to make the image larger, and I would like to not make it upside down. So the image I would like, the type of lens that will do that for me is a convex lens. Every magnifying glass you use is a convex lens. Okay, this last problem is a little bit tricky. A magnifying glass is used to look at a stamp. When the stamp is 4 centimeters from the lens, the image is magnified 2.5 times. What kind of lens is this, and what's the focal length of the magnifying glass? Well, a magnifying glass takes an object and makes it look bigger, makes it look larger. But it doesn't flip the image upside down, because that would make it harder to understand and understand what we're looking at. So I need a lens that will make a large virtual image. Well, there's only one lens that'll do that. The answer must be a convex lens. A convex lens makes a larger virtual image. A concave lens always makes a smaller virtual image. So I know every magnifying glass you've ever used is a convex lens. All right, so that tells me a couple of things. My focal point when I'm doing my math, well, it should come out to be a positive number because I'm dealing with a convex lens. But not just that. If I could be a little bit more clever, if I remember that I get a virtual image when the object is closer than the focal point to the lens. So since this stamp is 4 centimeters from the lens, my focal length should be larger than 4 centimeters. So that's something also to keep a look at. So let's solve for this problem. Now at first it might appear that you don't have enough information, but you do. Alright, so they tell me that the distance between the stamp and the lens is 4 centimeters. So I have P equals 4 centimeters. And they tell me that the magnification is 2.5. I want to find the focal length, so let me write that equation. 1 over F equals 1 over P plus 1 over Q. And right away I kind of noticed something. I don't know F, it's what I'm looking for. I have P, but I don't know Q. I have one equation here with 2 unknowns. So I need to look at another equation. That other equation is, of course, the magnification equation. So the magnification equation is equal to minus Q over P, which in this case it also equals HI over HO, but I'm not interested in the heights for this problem. Minus Q over P, and the problem tells me that this is equal to 2.5. Well, that means that Q must be equal to minus 2.5 times P. Well, I don't know what Q is as a number, but I know what Q is in terms of P. If I put that in there, then I'll have 2 things with P in it, and that's better than a P and a Q. So let's do that. So I get that 1 over F is equal to 1 over P. Now, but I gotta be careful with that minus sign. This is now going to be minus 1 over 2.5 P. Well, I need to solve for F. I know what P is, but I could put in the numbers right now and do it that way. But this is a good time to do a little bit of algebra. I know P is 4. I could put 4 there, and I could put 2.5 times 4 there, and then do out the math, and then remember to flip. But let's do a little bit of algebra. The common denominator between P and 2.5P is 2.5P. So I have that 1 over F is equal to, well, I'm going to put both of these under my common denominator of 2.5P. To make 1 over P with a denominator of 2.5P, this needs to be 2.5. Because 2.5 over 2.5P is 1 over P. And then to make minus 1 over 2.5P, I just need to subtract 1. So this is basically going to be 2.5 minus 1, or 1.5, divided by 2.5 times 4. So I get that 1 over F is equal to, 1 over F will be equal to 1.5. Well, 2 times 4 is 8, and half of 4 is 2. 8 and 2 makes 10. So the bottom of that becomes 10. So 1 over F becomes 0.15. Now, that's not the focal point. That's 1 over the focal point. So the focal point is 1 over 0.15, which works out to be about 6.67 centimeters if you don't round. And there you have it. Again, the focal point's positive. Should be. It's a convex lens. And the and it needs to be larger than the P. The P was 4. I was only 4 centimeters from the lens. That means that the object is closer to the magnifying glass than the focal length, and therefore the image should be larger and vertical. So everything works out. All right, so there you go. That's all we have for optics. We're getting very close to the end of the year and very close to the end of this term. So I'm glad you've all stuck with me throughout the course, and hopefully next year will be more of an ordinary, boring variety. We have this week's assignment, and then we have next week, which I'll probably do a mixed review of optics. I'm not going to start anything new this close to the end of the year. As you can imagine, there are no final exams this year. So get started on those problems right away. Email me. I'll probably, if I have a chance, I'll try to upload another video of some demonstrations of lenses this week to look at. But this should get you everything you need to get started on this week's assignment. So see you online. Bye.